Welcome, everyone, to today's Explainer. I am absolutely thrilled to be your guide as we explore what just might be the most masterful, perfectly optimized manufacturing system in the entire universe. And no, it's not a new tech factory, it's the natural world. For centuries, human engineering has tried to conquer nature, but today, we're flipping the script. We are going to look at nature as the ultimate veteran engineer. By the end of our time together, you're going to see exactly how biological evolution has already solved some of our absolute toughest industrial design challenges. First things first, to set our foundation, let's actually define our core concept. Green engineering is the combination of environmentally conscious attitudes, values, and principles with science and technology, all to improve global environmental quality. It's a fantastic goal, right? But how do we actually pull it off? Well, researchers have laid out 12 fundamental principles of green engineering. And in this explainer, we are going to map those exact 12 principles directly onto biology's evolutionary perfection. We're using nature's own blueprints as our guide. Okay, let's dive into our game plan. To make these 12 principles highly actionable, I've reorganized them into a logical 4-step product lifecycle. We'll start with sourcing, looking at materials and inputs, then processing for efficiency and prevention. Third is scope, where we figure out needs and limits. And finally, life cycle, covering durability and the afterlife of a product. Let's kick things off with phase 1, sourcing, materials and inputs. Every engineered product has to start somewhere, and how you source your raw materials totally dictates the environmental impact of everything that follows. In this first module, we're covering 3 specific principles: prioritizing inherent safety over circumstantial safety, utilizing renewable over depleting inputs, and integrating local flows. Think about human engineering for a second. We often rely on highly toxic, hazardous raw materials that demand massive complex safety protocols. That's what we call circumstantial safety. But Principle 1 demands inherent safety, meaning your inputs are just fundamentally non-hazardous from the get-go. Combine that with Principle 12, demanding renewable inputs, and what do you get? Photosynthesis. Plants and trees use perfectly harmless carbon dioxide and abundant renewable energy from sunlight. They use entirely safe, renewable raw materials to create byproducts that actually sustain life, rather than threaten it. It's genius. And that brilliantly illustrates Principle 10, integrating local material and energy flows. In industrial design, this means a system should hook into the energy and materials already available right there in its local environment. In nature, look no further than migrating shorebirds. These guys travel in massive flocks, constantly communicating and coordinating. They don't fight the environment, they read local wind currents, weather patterns, and food availability to optimally use the resources right in front of them, fueling an incredibly demanding journey. Which brings us to our active manufacturing phase. Once we have perfectly sourced materials, how do we process them? Let's move into phase 2, processing, focusing on achieving perfect efficiency and zero waste. We have 4 crucial principles to unpack here. Principle 2, prevention instead of treatment. Principle 3, design for separation. Principle 4, maximize space and time efficiency. And Principle 5, output-pulled processing. So, Principle 2 states that it's far better to prevent waste than to treat or clean it up after it's formed. We all know industrial cleanup is incredibly expensive and energy-intensive, but nature just engineers waste completely out of the equation. Take termites. They feed on dead wood, eating the cellulose and decomposing it entirely. They don't generate garbage that needs to be hauled away to a landfill. Their very existence is a zero-waste processing facility that actually enriches the ecosystem around them. Next, Principle 3 dictates that separation and purification should minimize energy consumption. Nature's solution here is wild, the flamingo. They have these unique beaks they use upside down, lined with lamellae and a large, rough tongue, perfectly adapted to separate mud from their food with barely any energy output. And right alongside that is Principle 4, maximizing space and mass efficiency. Just look at ants and aphids. Ants protect aphids right on the plants they eat, and in return, the ants consume the honeydew the aphids release. It's a localized, hyper-efficient exchange of energy happening in a remarkably small footprint. Now, before we look at our next biological analogy, let's clearly define our 5th principle. Output-pulled processing means systems are driven by immediate demand, a pull, rather than forcefully pushing inputs through a manufacturing line just because the machines happen to be running. So the crucial takeaway is that making products no one immediately needs is a major engineering flaw. Nature perfectly aligns with this. Consider the tiger. A tiger operates on a strictly output-pulled system. It only hunts when it's hungry, and it only hunts exactly as much as it requires right at that moment. When the output demand drops, when it's full, a tiger might walk right past its prey without batting an eye. Nature absolutely does not waste energy overproducing. And that concept of avoiding overproduction leads perfectly into our third major phase: scope, needs, and limits. This is where we examine nature's remarkably strict rules against excess capacity and unnecessary complexity. In this module, we're looking at two principles that govern those limits. Principle 8, meet the need, but minimize excess. And Principle 9, minimize material diversity. As a core rule of scope, listen to this. Designing for unnecessary capacity or capability, like those one-size-fits-all solutions, should actually be considered a design flaw. In modern engineering, we love building tools that do 100 things, even if the user only needs them to do one. Nature completely, flat-out rejects this mindset. Nature actually punishes excess capacity. Take the Asiatic lion, for example. Historically, they had a massive territory, ranging all the way from North India to Scotland. But today, they're restricted to the highly specific ecosystem of the Gir forest in Gujarat. When an organism or a product is overscoped or forced to operate outside its optimal environment, its viability shrinks dramatically. True specialization demands optimized environments. Then we have Principle 9, which requires minimizing material diversity to promote easy disassembly and value retention. Think about a modern smartphone. You've got glass, rare earth metals, plastics, all glued together, making it nearly impossible to pull apart and recycle. Compare that to echinoderms, like sea stars. They are complete, highly capable organisms managing locomotion, digestion, defense, and reproduction. Yet, they achieve all of this with incredibly low material diversity in their physical structure, simple ingredients masterfully arranged. Which brings us to a really profound question for any engineer or designer. What actually happens when an engineered system outlives its primary purpose? Does it just sit in a landfill for 10,000 years? Or does it feed the next generation of design? And that takes us to our fourth and final phase, life cycle, covering durability and afterlife. We're going to explore end-of-life planning, targeted durability, and commercial reuse, all through the lens of biology. Our final three principles address the sunset phase of a product. Principle 7, aim for targeted durability rather than immortality. Principle 6, conserve complexity. And Principle 11, design for a commercial afterlife. Principle 7 is a direct strike against things like single-use plastics that last forever. The goal is targeted durability, not immortality. A brilliant biological example is the elephant's trunk. It's extremely versatile, incredibly strong, serving countless uses from feeding to lifting heavy trees. But it is specifically targeted to be perfectly durable only for the natural lifetime of the elephant. When the elephant passes, the trunk breaks down. It's entirely durable for its purpose, but it is not immortal. Principle 6 tells us to conserve complexity. Basically, when you invest energy into creating a complex structure, you shouldn't just throw it away. Embedded complexity is an investment. Raptors demonstrate this beautifully. Instead of expending massive energy to build a brand new complex nest every single spring, they reuse the exact same nesting site year after year. They conserve their previous architectural complexity, just adding fresh material to strengthen it for the new season. Let's see how all this builds into our final concept. Principle 11, designing for a commercial afterlife. Just track the steps of a leaf. Step 1, leaves on a tree participate actively in photosynthesis. Step 2, their primary life cycle ends, they dry out and fall. Step 3, they decompose and mix with the soil. Step 4, that newly decomposed soil nourishes the very tree that dropped them. The leaf's performance in its afterlife is just as engineered and vital to the ecosystem as its life on the branch. We have seen how nature perfectly sources, processes, scopes, and recycles absolutely everything it creates. Which leaves us with this final lingering thought. If nature figured out sustainable engineering millions of years ago using these exact blueprints, why are we still designing for the landfill? I challenge you to take these 12 principles of biomimicry and apply them to whatever you're building next. Thank you so much for joining me in this explainer, and keep learning from the incredible world around you.